Hi, my name is Alex Alexandrescu and this is my entry for CECC2 Students Competition at MIT-X. My project is to control a DC motor with digital input. I would like to present you some of my tools. So one of my primary tools is this book, an old book about integrated circuits, CMOS circuits, so very useful for me. I'm also using a breadboard like this one here. I don't like to use those jumper wires that you will come with it, because the ends are too large, and if your circuits become a bit more complex, you won't have enough space to fit them. So I'm using just telephone wire like this one here. I cut it to all sort of dimensions just to fit in different holes on the breadboard. So it's a very thin wire, it satisfies my needs. Okay, so I have here a digital multimeter, a cheap one of course, and also I'm using 9 volts batteries, simply because I don't want to damage my circuits, just supplying them a lot of power. If I need a bit more power for DC motors, I use this rechargeable battery. Rechargeable batteries will give you a bit more current. I'm also using a sound card oscilloscope. It's a very nice application, a PC application. It uses your sound card input, the microphone input, as your signal reader. But the signal must also be limited. The threshold is plus minus 0.7 volts. So I made this little limiter here, and the schematics I represent it here. Okay, so here it's my voltage limiter. I've used the homework called diode limiter as an inspiration. So here it is. I have a resistor to limit the current in my circuit, and the 2 diodes for the diode limiter. And also I have here a voltage divider, and this is an adjustable resistor. You can get that using just 2 pins from potentiometer like this one. So you can vary its resistance, and the voltage will also vary accordingly. I've calculated these values for 9 volt input, so I know if I have a full 9 volt input, I won't get Vout voltage no greater than 0.4 volts. This is here, and if I divide that, I will have 0.2, 0.1 volts. So I'm on a safe side. I would like to talk about Zener diodes. These diodes here are 2V7. That means that they have a 2.7 volts breakdown voltage. So if we take a look at this spreadsheet, we see that the voltage breakdown voltage vary between 2.51 and 2.89 volts at a 5 milliamps current. If we go below or beyond that current, we'll get different values, and I want to illustrate this by using this schematic. I have here a variable resistor to vary the current through my circuit, and here it's my Zener diode, and I will measure first the current and then the voltage. What I have here is my little circuit using this Zener diode of 2V7, and if I read my output voltage, it's 2.7 volts. So I want to measure the current through the circuit, so I will measure that very quick. Okay, setting multimeter. Okay, so I have a current of approximately 5 milliamps, so I know it's working. Now I want to show you how a Christian oscilloscope works, and what I have here is just a basic oscillator using two inverters that can be found inside the 4049 integrated circuit, like this one here. It generates a square wave signal with a frequency in the audible area. So if I turn on this circuit, we should hear a sound. So let's do that. There is our sound. As I decrease the value of this resistor, the pitch of the sound will increase, which means that the frequency of the signal increases. In this side of the breadboard, I have an oscillator using a 555 timer chip. This is the sound card oscilloscope designed by Christian Zeitnitz. As I said, it's very useful for very low frequencies. And what I have there, it's the square wave generated by with the two inverters, and I increase my frequency, I decrease it. I also can adjust my amplitude and time. So it's very useful if you don't want to invest money in a professional oscilloscope, because it's not cheap, and for an amateur this is a fine solution. So this is the inverter oscillator, and here is the 555 chip oscillator. So I increase frequency. Of course there is some noise due to the sound card and all these connections and so on, but it's a very useful tool for amateurs. Okay, what I want to show you here are two MOSFET transistors. This one it's N channel and this one it's P channel. So I drive the gate through this potentiometer, the gate voltage through this potentiometer, and now the MOSFET is off, that's why the LED is on, and as I reach VGS, the LED will turn off. Okay, working. I'm connecting it to the ground. MOSFET it's off and it stays off. It stays, doesn't change. I connect it to plus and it's on. Okay. What I want to show you is that the parasitic capacitance will preserve the state of the MOSFET, and this is a characteristic of all field effect transistors. For example, if I touch this with my hand, my skin resistance is enough to discharge the parasitic capacitor. Okay, this was N-channel transistor, and I have here the P-channel transistor. You will see in the datasheet of these transistors, P-channel transistors, that they require a negative VGS voltage, but if we reverse the source and the drain. We'll put the load resistor at the drain, and the source and the drain is connected to the ground, and the source will connect it to the plus terminal. It will work as well. So here is the gate. Okay, I will vary the VGS, same thing. Okay, so I wanted to explain this because I will use 4 MOSFETs, 2 N channel and 2 P channel for an H bridge for my motor. What I have here, it's the 555 timer circuit. There are a lot of web pages that explain very well what I'm trying to explain here, and I will provide the links below. We can notice that we have 3 resistors with a value of 5 kilo ohms, and there's the name of 555. We also have 2 operational amplifiers that work as comparators. We notice that this has plus terminal connected to the resistive network, and this has the minus terminal connected to the resistive network, which means that when this operational amplifier will output a 0, this will output a 1. This little circuit, it's a flip-flop bistable circuit, which has as the name 2 states, 0 or 1. How this works? We notice that we can connect this little capacitor and these 2 resistors. The capacitor will start to charge through these 2 resistors, and when the capacitor is fully charged, it will trigger this comparator here, which will output a 1. This comparator here will output a 0, supposing that we provide 5 volts as a supply source. So this flip-flop will output then 1 on Q terminal and a 0 on Q inverted. So this will be inverted, this little transistor will be triggered, and the capacitor will discharge through this resistor here. We will have, when the threshold is reached, an output like this from 0 to 5 volts, supposing that we are supplying 5 volts to the circuit, and when the capacitor will discharge, we'll have a square wave output. So this is my schematic for the pulse width modulation, and this is the real thing. Please ignore this part, I will explain that later. I would like to mention that almost all my components come from old TVs, radios, so I reuse them. This DC motor comes from an old CD player, so everything is reusable, almost everything. This connector right here comes also from another battery, so I just opened the battery, I took this plastic and I made a connector. Okay, why using pulse width modulation? What is the purpose? Well, the purpose is to provide small impulses to my circuit, because in digital world we have zero logic and we have high logic. We don't have intermediate values. Then we will modulate the duty cycle of a square signal, so that the root mean square will have intermediate values for our voltage. Let me connect the DC motor to the circuit. So This is off, okay. Now it's on. Oh, sorry. As I am varying the resistor, I am varying the width of the pulse. So the root mean square of my voltage will also increase or decrease. Now let me to connect the sound card oscilloscope and to see what is really happening. Here is the sound card oscilloscope application made by Christian Zeitnitz, and we can see our square wave output from my 555 timer. I would like to mention that this application has also a spectrometer here, very nice. I can see that my main frequency it's about let's say 600 Hz. So by varying my resistor, I can vary the width of my pulse, the duty cycle. So my motor was spinning, but only in one direction. I want to be able to make it spin in the opposite direction, and here an H-bridge circuit comes in handy. You can find more about an H-bridge circuit on Wikipedia. This is just my explanation. Supposing that we have this circuit here, we have 4 switches, and we turn on this switch and this switch here. Then my plus terminal will be connected to the plus of the power supply and the minus terminal to the ground. So my motor will spin forward. If I will turn on this switch and this switch. My plus terminal will be connected to the ground and the minus terminal to the plus of the power supply. So my motor will spin in the opposite direction. This is one possible implementation of the H-bridge circuit. And by the way, the name of H-bridge comes from the shape of the circuit. It has the shape of the letter H. So we can see right away that I have a P-channel and N-channel MOSFET on the same branch. And so when one of the 2 transistors are opened, it's open, the other it's closed, and so on. And the same on this branch here. I don't want to connect my H-bridge directly to the ground, but instead I will connect MOSFET, because I want to drive my motor through my parts with modulated signal. Here is the circuit I will be using. It's designed by Rick Bickel. I found it on the web. So we can see it has 4 MOSFETs, 2 N-channel and 2 P-channel transistors. The gates of these transistors are driven by another transistor used as a buffer, and that transistor is driven by the output of an AND gate. I will be using, how I said, the NAND gates from 4011 circuit here, and this is the proper way to use a logic gate, a CMOS logic gate, because remember we almost must have potential. So when this switch is open, it is connected through this resistor to the ground. When the switch is turned on, I have plus 5 volts, 1 logic, so the output will be 0. I will be using a 4013D type flip-flop bistable circuit, like this one here. So we can see it has 4 terminals. I didn't draw the other terminals. The other terminals in my case must be connected to the ground. So we have a clock input and a data input, so we have Q output and the inverted of Q as an output. The flip-flop belongs to sequential logic, so I don't have enough time to explain, but as long as my clock turns from 0 to 1, it will my output will be the same as my D input. And if I connect my Q inverted output to the D input, when I will have a step signal for my clock, my output on Q won't change. Here it's how it works. This is 4013 integrated circuit. If I press once, my LED will stay opened. If I press again, it will be closed. This one here too. This is another little breadboard where I have my H bridge with the 4 MOSFETs and NAND gates inside the 4011 chip. So I will connect these two breadboards together to see my final result. So here is my final circuit. I've replaced the motor with 2 LEDs like in this circuit. So when I will have a plus on this terminal, this LED will light up. When I have the plus on this terminal, this LED will light up. So I will know when my polarity is reversed. So, let me turn on the circuit. So now it's moving one way and now the other way. And I also have one touch switch the other direction. And if I will vary this resistor, you see that the brightness of my LED will vary as well. This is my final assembly. What I have here is my motor in place. I know that many of you will say that I don't use a Schmidt trigger, but I don't have enough place for that. So I connected from my switches to capacitors to the ground to get rid of the bounce effect. So I turn it on, spinning in this direction. I can vary its turning speed. So, okay, in the other way, one way, the other way. I hope it can be seen. Just a bit more current. Also can go full speed. So this is my project. Thank you for listening. I would like to thank you also to all the teachers and to Ajwit, to Miriam and the others for organizing this amazing competition and making all this possible. I promise that in the future I will improve my English and my accent. And thank you again for watching and for your time.